255, and when fourth person will pass, then it will become from 255 to 0. And at that time point, I will have this overflow signal equal to 1, which will tell me, oh, we have detected 4 persons entering the room. So in this case, we don't need comparator anymore. We can just rely on the overflow, but then we need to initialize our counter with correct value, which is 252 in our case. So uh, you can actually also initialize it by saying, okay, put the value of -4 instead of like, because when you write -4, it is equivalent to FC, right? Because this is 2's complement of -4. So the counter will count 3 events to FF, like this one, 1, 2, 3, and the fourth event will be overflow. The fourth event triggers the overflow and the counter becomes 0. So 4 events are actually counted. Any questions? Okay, so we have seen in the previous slides that how we can use counter register or a register actually to count events or count some happenings, right? So we can actually also use a register to generate delays, right? So how? By connecting this input signal with, instead of with the sensor, we can connect it with the clock signal, right? And now clock signal is, a clock signal is running all the time, right? So it is not depending on any external event, like if someone is entering the room or how many cars have passed the particular location and so on, right? But clock signal is running all the time. So if clock signal is running all the time, our counter, what will happen is that every time we have a positive edge of the clock, the value of the counter register will be incremented, right? So this time what we are doing is that we are doing exactly the same thing, but we are using the clock signal instead of an event or instead of a sensor as an input for this up signal, right? So what we are doing is that we are initializing with FC, which is basically equal to -4, right? And then after that, after 4 o'clock, what will happen, that we will have an overflow, just like in the previous example. So we will finally reach to FF, which is 255, and then from FF to 0. So when that happens, what will happen, we will have an overflow. So here we will have an output of 1. So we can detect a delay of, when 1 appears, we can say, okay, now we have implemented a delay of 4 cycles, right? So because it counts 4 clock cycles. Any questions? So here we are just combining the what we have seen until this point, that is timer and counter. So we can use a generic timer or counter for generating delays, just like we have seen in the last slide, or to count events, or to generate waveforms, or to use capturing a signal, like, and use it as a stopwatch, right? So in this lecture, we are going to cover these two components, delay generation and counting, and we will see if we will have time to talk about waveform generation and capturing later on. But first, we will focus only the first two parts, delay generation and counting. Okay. So how we can use the same counter register, either as same register, either as a counter or as a timer. So counter is like, there is no how to say, big difference when you are using a register to count some events. So you are saying, I am naming it as a counter register. When you are using a register to generate delays, you will say, okay, I'm naming this register as a timer. Okay. So now here, so it basically only depends upon your, what is the input signal or the clock signal, what is the source of the clock signal. If the source of the clock signal is an oscillator, a clock source, so then you are saying, okay, my register is working as a delay generator. But if the input of the source of the clock signal is your external source or an event generator or an event happening, for example, a sensor, then you are saying, okay, I'm using my register as a counter for that event, right? So for example, you are simply putting a mux on the input, and then depending upon this control signal, so if this control signal is 1, so the external sensor will be connected with the clock of the counter register. But if your uh, select line, a control signal is 0, then your oscillator will be connected with the output, with the input of the clock input of the register, and it will act as a delay generator. And everything else, the basic operation is same, that whenever your positive clock arrives, the current value of the counter register will increment by 1. And when it reaches the maximum, it will overflow and the flag will be set equal to 1. Okay, any questions? Okay, so if no question, then let's go to the quiz, which is week 11, day 1, quiz 1. Okay, go ahead. Yeah, okay, let me stop here. Uh, okay, before I go to explain the answer, the thing is, I think the questions are a little bit vague. The question statement is vague, right? So counter operates on external clock. Actually, it should be counter operates on an external event signal or an external event, right? While the timer operates on the clock signal or the crystal frequency, right? So yeah, just if your answer, if the statement is vague, I just ignore it. But I just want to highlight the point that counter, it operates on an external sensor or an external event, while your timer operates on the clock signal. By internal clock here, basically we mean the same clock which is used by your AVR microcontroller. So timers are also using the same clock. So actually these statements will become clear to you or become more meaningful for you when we'll cover the remaining of the slides, but at this time point maybe they are not crystal clear. So just keep in mind that timers, they operate on the clock signal, and when we want to use a register as a counter, then it is controlled by an external event signal or an external sensor. Okay. So in Atmega 328P microcontroller, we have three timers. Actually, three timers are counters. Timer are because same time, same as we have seen in the previous slides. Same register can be used as a timer or as a counter. So timer is like when you are using the register for delay generation, and counter is when you are using the same register to count some events, right? So in Atmega 328P, you have three timer or counters which are named as timer counter 0 and 1 and 2, right? Two of them are 8-bit. So timer counter 0 and 2, they are 8-bit, but the timer or counter 1 is a 16-bit. So which basically mean that the size of the register is larger in timer or counter 1. So it can count for larger values, right? But 0 and 1 can 0 and 2 can count to the maximum value of 255. Okay, let's do the quiz, which is quiz 2. Okay, Go ahead. I'm giving you 30 more seconds. Okay. So Atmega328P has three timers. Actually, it is already shown on the slide, which is shared on the screen, right? And select the true statement. Timer 1 is 8-bit. No, timer 1 is 16-bit. Timer 0 is 8-bit and timer 1 is 16-bit. That is correct. Both timer 0 and timer 1 are 16-bit. No, it's wrong because timer 0 is 8-bit. Okay. Okay. So let's now talk about the timer or counter related registers in AVR microcontroller. And when we say AVR microcontroller, here we basically mean Atmega 328P, not other AVR microcontrollers. Okay. So the first register uh, is the timer or counter register. So actually this is the register which hold the values. So actually this register here, right? So for example, in timer 0 and in timer 2, it will be an 8-bit register, and in timer 1, it will be a 16-bit register, right? And here n means like it will be, n can be 0, 1 or 2, because remember there are three timer counters. So it's mean there will be three timer counter registers, right? Other than that, we have timer or counter control registers A and B. So again, here N means 0, 1, or 2, right? So for all of the three timer counter registers, we have associated timer counter control registers, right? Then we have an output compare register. So we will actually see the details of these, all of these registers, right? For example, what is the job of timer or counter control register? So other than in addition to that, we have output compare registers, and also they are two in numbers for each timer or counter. So that's why they are named as A and B. So and N will be again 0, 1 or 2, right? And then uh, Uh, okay, before I explain this one, let me explain the figure first. So here what will be happening is actually we'll have more detailed figure in next slide. So the output of the value of the timer counter register is compared with output compare register, and there are two A or B, and depending upon that we have an output flag which is set equal to 1. So if the two values are same, if it is not clear to you now, just hold for like 1 minute and we will see it in more detail. Okay. Other than these three registers, we also have a timer counter interrupt flag register. And again, it is a separate register for each of the three timer or counter register like TIFR 0, 1, and 2. And within this register, you have different flags. So you have a flag like timer overflow flag, which is, and then it will be 0, 1, or 2. And you will have output compare flag, so which will become equal to 1 when the value of the timer counter register will be equal to the value of the output compare register. And there will be also an interrupt capture flag in the same TIFR register. Again, we will see this register in detail again. And all of the timer related registers, they are byte addressable IO registers, which basically mean, so if they are byte addressable IO registers, and they are within the standard IO range, IO address range. So which basically mean that you can use in and out instructions with them to access them. So let's first talk about timer 0. Remember we said like there are three different timers, timer 0, timer 1 and timer 2. Timer 0 and timer 2 are 8-bit. So let's first talk about timer 0. It is an 8-bit timer, and it has a associated timer or counter interrupt flag register, which has three flags: uh, uh, timer overflow flag, timer overflow 0, which is set equal to 1 when the value of the timer counter register will overflow, which means that it will change from 255 to 0. When the value of the timer counter register will change from 255 to 0, this flag will be set equal to 1 by hardware, right? Then output compare match flag and A and B, we will talk about them in a minute. So here it is how it is working. So this is your timer counter 0 register of timer 0, right? So it will you can initialize it with a value, and then on every clock it will increment, right? And when the value will change from 255 to 0, then there will be an overflow, right? So when there is overflow, this will be set equal to 1. And then you have two output compare registers for timer 0, A and B. So here you can actually put a value, like for example, you put 100, right? And when the value of the timer counter register will be equal to 100, so every time on every clock, on every time when it is incremented, here you have a clock, every time the value of TCNT0 is incremented, and when it matches 100, so the result of comparison will be based on comparison, this flag will be set equal to 1, right? There are actually two compare register, output compare register uh, A of timer 0 and output compare register B of timer 0. So you can actually load two different values. For example, here you are loading 100. You can load here, for example, let's say 20. So this flag will be set equal to 1 when the value of your timer or counter register will be equal to 20. Okay. And then this timer 0 also has two other control registers associated to it, like timer or counter control register A and control register B for timer 0. We will have a look at how different bits of these two registers are used in a minute. Okay. Any questions about this slide? No? So the control register A and control register B of timer 0, let's have a look at them. So the so both of them are 8-bit registers, and actually they are used together to configure your timers, like for example timer 0, right? So let's look at first at this table. So these bits, WGM 0, 1 and 2. So two of these bits are in register A, and the bit number 02 is in register B. So these three bits together, they define the mode of your timer. Your timer can actually be used in different modes. It can be used in a normal mode, pulse width modulation mode, CTC, which is clear timer on compare match mode, and fast PWM, reserved, and so on and so forth, right? So we will be basically covering only two modes, normal mode and CTC mode in this lecture. And then we will see if we need to cover the pulse width modulation or not. Okay. So for example, normal mode is when you like your counter increments on every clock, and when it reaches the maximum value, FF, and then on one more clock when it overflows or changes value from FF to 0, your overflow flag is set. That is known as the normal operation, or the normal mode. So on every clock, your value of the register is incrementing until it reaches maximum, and then it overflows to 0, right? CTC mode we will cover today, hopefully. So this is how your normal mode work. So whatever value you have put initially, let's say you have put initially the value 0 in the register, and then after that you start the counter. So on every clock, the value will increment, like from 0 it will go to 1, 2, and then it will finally reach the maximum value FF. And then at FF, when another clock arrive, it will go back to 0. And at this time point, your overflow flag will be set equal to 1. Okay. So if you want to simulate this one, it will look like something like this. Initially, you have 0 as an 0 for the overflow flag of the timer 0. And then here in this graph, uh, on the x-axis you have time is increasing, and on y-axis you have the value of the TCNT0 or timer counter 0 register, right? So let's say you initially put the value in 0, and then you said, okay, you repeatedly provide the clock signal, right? So on every clock signal, what will happen? The value will increase from 0 up to 55, right? So the value will continue increasing until it reaches maximum, and at that point it will overflow and be set equal to 0, and your flag will be set equal to 1. Then you need to actually override the flag in your program. So you need to set it back to 0. If you don't, it will not be automatically set equal to 0. So you have to, in your program, you need to take care of that, right? So, and let's say you set it equal to 0, and again the clock with the clock, the value will continue increasing, and again when it reaches 55, again the flag will be set equal to 1 by hardware. Okay. So this is how your normal mode works. Any question here? And one more thing, which is maybe not highlighted here. In this figure, we have shown that, okay, the initial value is 0, but initial value can be anything. For example, you can initialize the register with 2 and then enable the timer. So what will happen, that it will start counting from 2, 3, 4, 5. Or you can, let's say, initialize with, I don't know, the F0. You initialize with F0, and then on every clock will start incrementing F0, F1, F2, and finally FF, and then it will go back again to 0, and then 1, 2, 3, 4. Okay. So, okay, let's have a look at an example. Let me check the time. Okay, we have some time. So, yeah, today is Tuesday. You don't have an quiz, right? Okay. So write a program that waits 15 machine cycles to toggle PB5 in normal mode, right? So it means that we need to actually initialize this register, right? Such that after 15 cycles, the register overflows, right? So we have this flag equal to 1 after 15 cycles. So it means we need to know that which value we should put in this register, right? So if we convert 15 into the hexadecimal form, it is F, right? So when does the overflow happen? So overflow happens when your value of the register changes from FF to 0. So what we can do is that we can initialize the register 15 values less than FF, right? So what is FF in sorry. So what is the so when does overflow happen? Actually, let me make it more simpler for you. You can actually do it in the decimal domain, or in the decimal form, which will become more easier, right? So what is the maximum value? 255, which we can hold. But what are the total different numbers which you can hold? They are 256, because we are starting from 0, right? So what you do is that you need 15 machine cycles. So you subtract 15 from this one. So when you subtract 15, what will you get? To do the math. I'm so bad on that. Let me do it on the calculator. 256 minus 15, 241, right? So what you need to do is like that, you can simply put 256 minus 15, and that was 241, right? So you can simply load the register with 241 and then you can start the timer. So it will take 15 cycles. If you initially have this value in the register, it will take 15 cycles to overflow, right? 14 cycles from 251 to 255 and then one cycle from 255 to 0. Okay, so it will become in total 15 cycles. So F1 is actually nothing but the value of 241. Okay, so you need to simply load the value of F1 in this counter register. And then other than that, what you need to do is that you need to select the clock. Remember, the clock is coming from your clock is actually coming from oscillator, but not directly, or your crystal, but not directly. It actually comes through this circuitry shown here, right? So here, this is timer counter zero clock source. Actually, this is connected at this point here, right? So you need to select which one of these inputs on the mux you want to connect on the output, right? So what options you have? Zero, which mean no clock, which mean your your timer will not work because you are not providing clock. So actually you will be having no clock on the output. So timer will be disabled. One, when this one is connected on the output, so it has this, it's mean the your timer will operate on the same clock frequency as your microcontroller is working, right? So if your microcontroller is, let's say, working at 8 megahertz, your timer will also operate at a clock frequency of 8 megahertz. And then the next options 2, 3, 4, and 5, they are simply how to say slower clocks, like you are dividing the frequency by 8 or by 64 or by 256 or by 1024. And 6 and 7, these are actually, you are saying, I don't want to use a clock, I want to use an external event or an external sensor. So you are basically saying, I want to use my register not as a timer but as a counter. Okay, so how we specify, so this is the how we specify the specify in register, control register, that which clock we want to use by using these three bits: CS00, CS01, and CS02. Here we want to, in this example, we want to use the same clock frequency on which our AVR microcontroller is working. So that's why we are selecting 1. So 3-bit binary of 1 is 001. Okay. uh, yeah, let me stop here because we are left with 2 minutes, and I will be covering this slide again in the next lecture. Okay. Any questions at this point? No. Okay, if no, then lab 7 is released. I released it yesterday. I know I'm late, but it is not difficult lab. Things are straightforward. There's task A and B, they are already implemented. You just need to run them, download them, and run them. And you just need to understand them, how they are working, look at the code. And task C, you need to implement it, but it is very easy to implement if you already understand that how task A and B are working, right? So try to finish your lab today. I will be willing to give you the extensions, but I will strongly encourage you to not ask for it because then it will affect your timing for submitting the next lab. Okay. So that's it for now, and see you in next lecture.